Welcome back to DSP, and this is our last week of lectures. Thank you for, apologize for the delay. So I was stuck in a meeting. It was a admission meeting. Admission, you know, 招生放榜啊. Tomorrow will be the announcement of college application, 个人申请二阶放榜啊. So there, the university always has a meeting like that to make sure that everything is correct. So all the department chairs have to sign the form to make sure that all the names are, and all the order, 放榜名次的 rank is correctly printed. So we'll do that tomorrow. Okay, so yeah. So that's why that's an important meeting. So there was a delay. I apologize for that. But then because of delay, I decided that this last lecture is not going to be included in next week's final, just to make our life easy. But it's fun stuff. It's interesting stuff. I just want to ensure that if you wait for me, you got the freedom to decide that maybe your time is precious. You can go elsewhere. You can skip this lecture. That's fine. But in the meanwhile, this lecture will be very much about your homework number 5. In homework number 5, there's the computer part, right? So I uploaded a file which contains telephone tones. And I ask you what numbers they are, or what is the phone number, right? In case you haven't taken a look. So that's homework number 5, the computer part. You're asked to answer what's the phone number. Right? You know, whenever you dial a phone, you hear beep, 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 the beeping sound, right? So actually the sound will be part of our topic today. So today's topic is an introduction to what I call spectral estimation. We estimate something, a few things from a spectrum, and that is called spectral estimation in the frequency domain. Estimation in the frequency domain, using what? Using short-time Fourier transform, okay? So as a part of motivation, this is a telephone pad, and there's an array of 4x4. Usually we don't see these anymore, okay? I haven't seen the last column at all in my life, but this is an image I downloaded from the web. So which explains that actually the idea is very simple. Each time you press on a button, 2 tones, tone 就是那个纯音啦，就是 a sound with single frequency. That's called a tone. You hear a combination of 2 tones. It's fairly easy. So each row here, 1, 2, 3, that's the first row, second row, third row, last row, each row corresponds to one of the 4 frequencies. And each column, similarly, usually we have 3 columns nowadays. Just you can forget about the last column, but the standard was made over there. So theoretically, you could also use the 4th column. But for the 3 columns we typically see on the phone, each column corresponds to 1 frequency. So for example, you press on number 5, you should hear what you are going to be hearing is a combination of 770 hertz and 1336, 2 frequencies. Easy enough? So just to give you an idea, so I prepared a few files. So for example, 770 sounds like this. That's 770, okay? And 1336 is like that. So can you now, I ask you to imagine what does it sound like when you put the 2 tones together? Can you imagine in your head? For those of you that are more musically inclined, 如果对音乐比较有感觉的话, you're more musically inclined, can you imagine hearing these 2 at the same time? And that, can you imagine that? You will have some sort of interval, okay? So when you play them together, indeed, that's number 5. Number 5 is this. So it's a very simple idea, okay? That's how technology advanced in the past. The phone pad, each button corresponds to a combination of 2 tones. We use the frequencies to encode which button has been pressed. Okay, so far so good? So it's fairly easy in case you're interested. Seriously, I use this a few lines to create the combination tone. So I have y1 a sine frequency 1 of t, y2 equals to a sine frequency 2 of t, t being a few seconds. Yeah, 1 second actually. Yeah, 1 second. Duration is 1 second. So 1 times the sampling frequency, that equals to 8,000 samples. Yeah, so time goes from 0 to 7999, right? Exactly 1 second. Yeah. So in this, you can just easily create a dual tone and that's the result you're hearing. Okay. Yeah. Fairly simple. So a bit of history. Have you ever wondered why the buttons need to make sounds? If I ask you, it's an open-ended question. Have you ever wondered? Have you ever wondered in your life? 侦探里面有演哦，那在他演之前，你有 ever wondered? Has anybody you yeah? 什么帮什么？视觉障碍 That's a good point. So you mean that if you're visually impaired, you should be able to just press the button and make sure by listening to the sound. That's a good point. What other have you ever wondered why do buttons need to make sound? What if they don't make sound? It's just a button on and off, right? Why not? I think my answer is that you remember the telephone line is an analog system to begin with, in early days. So all the infrastructure analog communication, okay? So in the past, it used to be like you talk to the phone, your voice is analog. And everything is transmitted through the landline in analog fashion. So in the old time, if you need to encode the number, and you cannot do it digitally, how would you do that, okay? You might need to convert everything into sound first, because voice is sound. This entire system, the entire transmission system is designed for transmitting sounds. Okay, so that's why you also need to encode the button in as a combination of some kind of sound. And the easiest way they figure out is a combination of 2 tones. Okay, so that's my part of the answer. For the visually impaired, I think it could be interesting. Maybe we can all learn to hear the sound and be able to tell the phone number. That'll be a special talent. Okay, 可以在电机之夜表演and that you know what this is, right? You're not that young. Have you ever called on public phone like that? You need to insert coin. You have the idea? Do you have any idea? You're not that young. 电话卡已经是比较后来的，更早都是投币，And you can imagine that if you call international call, early days, 1980s, so you make a phone call to the US through the public phone, you prepare like $100 coins. You keep inserting every 3 seconds. I'm serious, don't laugh. That's what happened all the time. When you make a phone call to your friend in America using this, you go to the bank first and ask for a bag of $1 coins. Or yeah, you can insert $10 each time. Yeah, so you just keep. That's the old time. Okay, public phone buttons. There was one almost 10 years ago. We still have one of the phones on campus. Okay, yeah. So the system. So that's a bit of history, and I have a story to tell. Actually, when I was in high school. My friend used to have a watch like that, a smart watch. Back then, Casio, made by Casio, the Japanese brand. There are buttons, right? And the watch, okay, can make sound. So somehow my friends showed me that they were able to hack this system. You can pick up the phone and then play a sequence of 2-tone combinations to the receiver, and somehow in that way you can bypass the need to pay. It used to work sometime around 1990, but later very soon the government found out this is a漏洞, so they fixed this problem. So after that we could not do that anymore. So seriously, the phone number is encoded and transmitted using sound, using a combination of 2 tones, okay, in an analog system. Okay, so in this lecture, I would like to cover in more detail this classic dual-tone multiple frequency technology. That's the name, dual-tone multiple frequency technology. And imagine that now if you are somewhere in the path of transmission and you need to decode the phone number in order to route the communication, routing, right? Yeah, because your phone call is meant to be delivered to somebody who owns that number, right? So as far as routing, 就是路径要怎么排 is concerned. Everywhere along the path, there's need to decode the sound back into phone number. Okay, so imagine you need to do that, and that's your homework. Okay, so I suggest that this can easily be done by DSP. We will use short-time Fourier transform, and chances are you by correct choice of window, and by being careful about the resolution, frequency and time domain resolution. We began that the topic last week. So by careful choices, you will be able to decode the phone number while receiving the tones. Okay, and then there are two. I don't know if I have time today to cover into details, but this is a borrowed lecture from my graduate level course. I have a graduate level course called Audio Signal Processing, basically. So this is one of the lectures right there. So in that lecture, and this is a copy from that lecture, so we have an issue of two very similar ideas: resolution versus accuracy. In Chinese, resolution 可能可以翻译成什么解析度啊 right? But accuracy, I claim, is has a slightly different notion. 那个意思不太一样。Accuracy 是准确度， but resolution 是解析度啊。So your estimation can have a high resolution, can be based on high resolution representation, but it lacks accuracy. Can be really wrong with high resolution. So the two terms have different notions. And they deal with the main problem is interference versus noise contamination. Every recording has noise. That's a point that we haven't really been talking about throughout the semester. Every recording of any kind of signal has noise, right? So when your signal is contaminated by noise, how could you ensure you estimate, let's say, the frequency? 770 is the frequency. You estimate the frequency accurately. So that's a concern, okay? So noise is always a concern, and it affects accuracy. So we have a part like that. And then it turns out that this is really, really advanced. Okay, so Fisher information and Cramer-Rao bound. I think I'll skip it for today. All right, so the first thing, let's begin. Spectral estimation. And we talk about decoding the dual tones. Okay, so you have for the number 5, a combination of two frequencies, and this is a plot in the frequency domain, in the time domain. That's a waveform. That's a waveform of adding a 770 Hertz tone with 1336, a combination of two tones in the time domain. Okay, and the time now we're looking at about 20 or 30 milliseconds. Making sense? Does it make sense? This is what happens in the time domain. All right, so how do we estimate the signals, the frequencies? If you just look at the time domain, it might be tricky. Yeah, I told you this is number 5, so you know the answer is that, right? But can we agree that in the time domain it's quite tricky to figure out what the two frequencies are? I don't have a really good answer to that. Okay, maybe you can do it in the time domain, but this is what we're going to suggest. Okay, we do it in the frequency domain or in the time frequency plane. Right. So let me explain. So first, we would take the input and discretize it into digital format, and then we apply a window. We apply a window, so the window has a length. And then we use what we learned last week, the fast Fourier transform, to go to the frequency domain computationally. Okay? You multiply your input with the window. Let's say if, for example, if this is a window, you can imagine multiplying this bell-shaped window, which must be a Han window, with your signal, you get a packet of some sort. Okay, you get a wave packet that's focused around this time, centered around this time, and the window length is nicely set at about 20 milliseconds in this example. So you multiply your window with your input, and then you expect, then the question is, what do we expect in the frequency domain? Suppose we can assume that there is a combination of two tones, and the only unknown is the frequencies. Suppose that we can just safely assume that there are two tones, it's just the frequencies we don't know, right? If you can make that assumption, how do we estimate which two frequencies are they? How do we do that? What do we expect to happen when we multiply that unknown signal with a window and then go to frequency domain? What do we expect to see? What do we expect to see? And that's your homework. That's homework number 5. Okay, what do we expect to see? So if you can see something, then maybe you'll be able to figure out which button is pushed. Okay, now which button is pushed? So a bit of math, all right? It's actually not that hard. So suppose that we've already assumed, this is by assumption, if Xn really is a linear combination of two tones. Suppose that's true. Okay, suppose that's true. Now, suppose what's being transmitted on the phone line before the voice communication started, there must be nothing but the phone number, right? The voice hasn't come in yet, right? Yeah. So suppose that we really can assume the signal is a combination of two tones with amplitude A1, A2, also unknown, and cosine, phase unknown, phi1, phi2. Frequencies are also unknown, F1, F2 in hertz, where this T, big T, is the sampling period. 是取样时间啊. Big T is the sampling period. So far, so good. Can we agree that this is a very general form for a combination of two tones, two pure tones? That's what a tone means. A tone means cosine. A amplitude cosine of one frequency, maybe a phase shift. Okay, unknown turns out to be unimportant phase shift. No, phase 不是很重要啊. Phase is not important. So far, so good. Can we agree that this is a linear combination of two tones? Then let's jump to a conclusion first. We expect that if this is really Xn, then its Fourier transform we know. We already know that by now you should be familiar that the Fourier transform should be the spectrum of X. Okay, again I'm using a sloppy notation. X. Let's say if this big X denotes the spectrum, the Fourier transform, the DTFT, then we know that the DTFT should be amplitude times divided by 2 plus times EJ phi 1. Okay, and the intermediate state is because cosine is a real part of cosine is a real part, right? The real part must be itself equals to itself divided by 2, right? Plus divided by 2 plus their complex conjugates, which I haven't written. I didn't bother to write it down right there. This is just changing cosine into 1 over 2 EJ something. Okay, you all know how that goes, right? So therefore, the Fourier transform, if you just go directly, by the way, we haven't applied the window yet. This is just assume that the button has been pushed down forever. Okay, let's assume that somebody pushed the button and forever. Okay, yeah, for the ideal case, that's what it means. We have a signal in time which is there forever. Okay, for now. So then, since it's pressed down forever, the Fourier transform is delta function, right? It's a combination of delta function located at omega 1 and omega 2 respectively, plus their negative frequency components. There's another one in negative frequency range. Okay, so I'm missing a few things. So here, apparently omega 1 equals to what? Omega 1 equals to 2 pi f1 t, or it equals to 2 pi f1 divided by fs. Yeah, if that looks more familiar. And similarly, omega 2 equals to 2 pi f2 divided by sampling frequency. Okay. So far so good. So this is just good. Oh, we know that the pure tone corresponds to delta function. Okay, and that's an important concept. You have a pure tone in time, right? You have a pure tone in time with frequency of f0 equals to 1 over something. 1 over its period. Single tone, so that when we go to the frequency domain using DTFT, you expect the answer should be, there's one component right here, another component right there in the omega domain, right? Where you should expect in omega 0 and minus omega 0, okay? Or let me say, just say 1, okay? T1, 1, 1. So that's what you will see in the frequency domain, this being x in the time domain, this being big X. Usually we write EJ omega, okay, throughout the semester, but I'm being sloppy. 我这边是用一个比较简洁的 notation. I hope you don't mind without confusion, okay? So far so good. So that's the important first thing to notice. Realize that a tone is very simple in the frequency domain. Cosine is so simple in the frequency domain. Just delta function, okay? One right here, one right there. Yeah, that's a combination. That's one tone. That's one tone. One tone equals to one component right here, one component right there. Okay, yeah. So if you understand that, then we are ready to apply the convolution theorem, okay, of the second kind. Okay, so that's the next page. So how about now short time Fourier transform? This is good old DTFT, not yet short time Fourier transform, just DTFT. So then you can ask, how about the short time Fourier transform after windowing? After windowing, okay? How does this relate to the spectrum, okay, the DTFT? How does the short time Fourier transform now as a function of both frequency and time shift, how does that relate to this, this simple fact? So next part, now we know that x is just written as cosine, right? Cosine is one component right here plus their complex conjugate. CC stands for complex conjugate. Okay, let me write it down. CC 是 complex conjugate, 共二复数的部分 complex conjugate. Now, when we multiply our signal with the window and then take the Fourier transform, this is what we get. We get the Fourier transform of the window but shifted to that frequency. So remember Fourier transform of the window, okay, rectangular window, Hahn window, Hamming window, or if you will, Kaiser window. Why not? Yeah. And this is a shift theorem, okay? Because our signal is a pure tone. So in kind of communication jargons, in communication terminology, you can imagine that this is a carrier and this is a message, okay? So this is a baseband, the window is long, and now we have a carrier of a frequency which shifts the spectrum to where its frequency is. This is shift theorem. When we multiply x with w, then take the Fourier transform, we are modulating w, the spectrum of w, to that frequency with the adjustment for the magnitude and phase. Is this clear? Is it making sense? Does it make sense? And similarly, because of the presence of the second tone, we are also modulating the spectrum, or shifting the spectrum of the window to this other location. Okay, shift big W to the right and to the right, and also to the left, because there are the negative frequency components. Okay, so in the end, so we can compare the DTFT and the spectrum with windowing. The only difference is that we expect to see a spike delta function at omega 1 and omega 2. But similarly, we expect to see not a spike, but now a copy of the Fourier transform of the window, also centered at omega 1 and omega 2, centered. 它的中心点在那边。Yeah. So that's our idea. That's what's going to happen when we apply a window to multiply our signal. And we know that our signal is a combination of two tones, okay? Combination of two tones. I hope this is making sense to you, okay? So that is to say, if our signal xn is A1 E J omega 1n, if that's our signal, and then we multiply our signal with a window function, okay, with a window function, then the Fourier transform of x with a window, if you take the Fourier transform, you expect to see the spectrum, a spectrum which also has two components. One is located centered around omega 1, and the other one is a negative frequency part. And you expect to see a copy of the Fourier transform of W. So let's say this is the Fourier transform of, this is the magnitude, okay? So you expect to see a main lobe and side lobes. That's probably one thing I really want to point out, okay? You expect to see the main lobe of your window function, as well as side lobes. There's going to be some side lobes extending in both directions. And similarly here, you have the main lobe and side lobes, okay? This is what we expect to see just by using basic shifting theorem, okay? Shifting theorem modulation, okay? This is what we expect to see. So instead of seeing spikes, we see a main lobe, which has a finite width, okay? Which has a width, and you know that the width is inversely proportional to the duration of that window. Okay? This is what you expect to see. Okay, so as a summary, so in the time domain, we multiply our signal with a window, and then when we quickly go to the frequency domain, because we have two tones, we expect to see one component around omega 1, another component around omega 2. Okay? So this is what we end up seeing. Okay? This is what we end up seeing. Exactly this Fourier transform, after we window the signal, and the signal has two tones, we expect to see a main lobe, pretty tall, a tall main lobe. But if you look closely, there are side lobes. These are the side lobes. That's around right here, around that right there. Yeah. We expect to also see some side lobes. But otherwise, the main lobe, we see two big components. One big one located at omega 1, which is, if you convert the frequency axis back to hertz, oh, this must be around 700 something, right? You can tell. You can see a big main lobe right there. Another big main lobe right there near the intended frequency. Okay, so in the frequency domain, we will be able to estimate the tone frequencies by looking at the location of where we have peaks. Looking at the location of peaks, spectral peaks. And this is the process what we call spectral estimation, we're estimating some kind of property of our signal in the frequency domain. So that's why we call it spectral estimation. 频谱上面的一种估计一种估计All right, so I believe in the homework, in the starter code I gave you, there is, but this is just not yet short-time Fourier transform. This is one frame, one spectrum. Okay, in short-time Fourier transform, remember that big X, omega, n, m is defined as summation. Now let's say the index is still n. Xn. So I remember in the last lecture I suggest that we shift our time, our signal to the left by m samples. Okay, and then we fix the location of the window and then take the short-time Fourier transform. That's what's meant to perform a short-time Fourier transform. Shifting our signal to the left by m samples while taking the Fourier transform of the window signal. So that's why the result is not both a function of omega, it's a time-varying spectrum that we're going to be seeing. So I remember that in the homework I gave to you, if it's already started, there's the 3D plot that I made. There's 3D plot, and then in this axis we get the frequency, in that we get f, and also I'm showing to you the magnitude response, magnitude of x omega m. Okay, so check it out. So check it out. So we have a plot like that, and you're free to drag the 3D plot in MATLAB and see the short-time Fourier transform, the spectrogram from different angles. Okay, I hope that is helping you to now turn this into a 3D representation. Have you started? Homework number 5? Okay, so we have used the kind of shift theorem. We're multiplying our W is being carried by our tone. So consequently, the spectrum is a simple shift in the frequency domain. Okay. So I think this should be pretty clear. So now, the issue of window, issue of choosing the window. Okay. So if you agree with me that we expect to see main lobe and side lobe, so then your choice of window would make the result look different. Okay, not only here but also in your homework number 5. In part of the homework number 5, I asked you to try to change the type of window. If we just fix, for example, on this page, when we fix the window length to be 20 milliseconds, but we can choose in between rectangular window and hung window, the results will look different. Okay? The result still, you are going to see the two tones, two peaks right there. But the side lobes are much more prominent, 更明显了. The side lobes, when you use rectangular window, the side lobes are much higher, much larger, much higher, much more prominent, 更明显, much more obvious than using hung window. Yeah, can we agree on that? Did you notice? Right? And what else? What's the other difference? Is there something else is also different? How about the width of a main lobe? So again, we see over and over. Before we were using window for filter design, but this is another context where windows are used. Okay, in the entire semester, we talk about using windows for designing FIR filters. That's a totally different topic. Here we're talking about spectral estimation, but also because of the nature of trying to visualize something on the time frequency plane, you got to choose your window. Depending on your choice, rectangular window has a narrower Narrower main lobe, which means the spectral resolution is higher. Okay, narrower main lobe. The main lobe is not fat. It's the narrowest. Okay, but then the side lobes are more prominent. Okay, side lobes are more prominent. 比较明显. Side lobes can be much higher than if you use hung window. Okay, and similarly, you can just replace the hung window further with a Blackman window. What do we expect? When we use a Blackman window, also 20 milliseconds, do we expect to see the main lobe, even wider main lobe or anything? Okay, do we expect the side lobe to be further suppressed, even better, smaller than that? Okay, so that's kind of now it's a question that can be you can discuss, right? You can discuss that. Choice of window matters. It affects two things. One is the main lobe width, and the other is the side lobe height. Okay, the height of the side lobe, the width of the main lobe. And here I do have a few comments. So in spectral estimation, if the goal is to identify all sinusoidal components, so there's a subtle difference. Let me try to explain. There are two different kinds of tasks. Okay. In one kind of task, like for example, in today's task, if we know a priori, if we know beforehand, okay, a priori just fancy word, Latin word for beforehand. 如果我们事先a priori, yeah, you should have told me a priori. 你应该不早告诉我. You want to be really fancy. Tell somebody to tell you next time. Tell me earlier rather than. If you don't know, if we know a priori, we know beforehand in advance that there are going to be two tones. Such like we are on the telephone system, right? We can very safely assume either a button is pressed or a button is released. Can you simultaneously press two buttons? Can you do that? Have you tried that as a child? 小时候有没有尝试想要同时按两个电话号按钮 ？Anybody? 有没有这么白目，这么中二？ I think they designed it so you cannot press. I'm sorry. I'm pretty sure you cannot press the two tones at the same time. Okay, but so we know if we know a priori there are at most two tones or there's no tone, right? It's fine. So if there are at least at most two tones, then actually I would recommend using rectangular window. Why? Because it has the best resolution. You look at the main lobe; it's very nice, very narrow. Okay. We know a priori that we are looking for two tones in the spectrum. Which two tones are? They must be this one, the biggest one, and the biggest one, right? Must be them, nothing else. We know a priori that they are at most two tones, okay? So we know that, there are two tones, one at this frequency, the other at the other frequency, okay? Everything's easy. So that's our task. Our task is a simpler task. We can, by assumption, assume that we know beforehand there are at most two tones, okay? But imagine this. How about if there is a more difficult task where the number of tones is unknown? 如果我们没有事先知道有几个 pure tone 的话that's more tricky. The task becomes trickier. Why? Let's say if you apply short-time Fourier transform, and when you go to a frequency domain for any single at one moment, you look at the short-time Fourier transform, it looks like that, the magnitude, okay? Can you safely tell me that there are only two tones? Can you be sure? Are you sure there are only two tones? Simply by looking at the frequency domain result. Can we just be so confident that there are only two tones and nothing more? What if somebody tell you that, okay, I took a look, and there's a big tone right here, another big tone right here, plus a sequence of smaller tones right there. Yeah, right there. Are they wrong? Are you? Yeah. How can we tell if that's wrong? You see, yeah. when we do not know beforehand there are two tones, then this becomes trickier. Then there's no simple way for you to oh no, sorry, this is there's a peak, but it does not correspond to a tone. It's just a side lobe of this main lobe. Then you need some extra effort to examine that. Okay? To exclude the possibility that there really is a smaller tone at how many dB? 4 dB, I don't know. If you're seeing a big tone at 24 dB of magnitude, oh no, not 24 dB, but 24, right? Linear scale right here. You can hardly be sure that there isn't a tone at this magnitude, whose frequency is close to 770 but higher. Let's say 790. Okay, I don't know, right? So you cannot be sure. So it's pretty confusing. Okay, it could be pretty confusing. So imagine that instead of analyzing telephone buttons, you're analyzing a piece of music, real music. Let's say you plug your guitar string. The string's making sound. There are going to be a known number of tones because of this guitar. Okay, then it becomes hard for music transcription. 要采谱就没有那么简单了 for music transcription. Okay. So you need to kind of think twice before adopting the rectangular window. So in that case, I do not recommend using rectangular window because of the trouble that the high side lobes are giving to us. There is definitely trouble, okay? When we try to interpret what's inside this spectrum. Is that making sense? Without knowing, we do not know in advance that there are two tones only. Okay. So in that case, I recommend not using rectangular window. Okay, maybe using a Hahn window. And you know that. Let me go back a few slides. Using Hahn window, even though the main lobe now becomes wider, we said the spectrum is smeared a little bit, 有变抹到两边去。But the splattering. 这是有名字的啊，这些都有名字。To widen the main lobe means the verb to smear. Smearing versus splattering. Sometimes in the field of audio, people talk about smearing, spectral smearing, spectral splattering. 这两个字蛮有意思的啊。Smearing, splattering. Smearing means to widen the main lobe in this context. Splattering meaning that we have another side lobe that goes that's outside the main lobe region. Smearing versus splattering. So that's a choice of window. What I'm talking about? Okay. So anyway, so the choice is up to you, right? It's just up to you. If you want to ensure that there's no splattering, then choose Hahn. But if you want to just maximize the resolution or to make the main lobe most narrow, then you use the rectangular window. Okay, so that's kind of the guideline for choosing the window. So far so good. I think I'll just continue talking. Okay, so a question for you. Now question time. Smearing, splattering. 英语教学时间。What does these words mean? Smearing 造句。有人会用 smear 造句吗 ？Smear 跟 splatter. You can also, check. Let's take a break and please check what's the meaning of smearing versus splattering and tell me. Make a sentence. Find a sentence. Smearing or splattering. What does that mean? 这有点帮助我们了解啊。为什么？其实我觉得我们在学科技那个英文还是蛮重要的，因为很多的名词它会取得比较活灵活现的。如果用英文来去理解那个名词取得，其实有时候蛮有趣的，是很活泼的。科技英文是可以很活泼，通常我们觉得科技中文会比较严肃一点。好像你讲所有东西都很严肃，但英文有时候它原用语是相当的活泼的。OK, I'm just I was just saying that sometimes these jargons in English, they have pretty vivid meanings. Okay, it's not at all. Not at all. So it's not always so serious the way they name things. 好吗 ？Splattering. What does it mean to splatter? It's a verb. Splattering. Anybody splattering 什么意思？什么意思 ？Splattering 什么意思？飞溅。飞溅哪个溅？水字旁。It's like imagine there's a pot of water and it's been raining these days, right? If you just intentionally step on the water and to make the water splatter, to scatter the water all around you, that's what it means to splatter. 这个撞声字啊，I don't know the term. Splash, splatter, 这一类的都是这种切开啊、分开啊、这种意思啊。To split, right? 所以这类的 SPL splattering. Okay, spectral splattering. Imagine that now the energy is scattered around away from its actual. That's a spectral phase. This is a fancy way to refer to the side lobes. Okay, a fancy way. This is a fancy term. How about smearing? Smearing anybody? What do you mean to smear? 磨过去，橡皮擦 ，smearing， 橡皮擦磨过什么呢？磨过表面啊，是颜料啊，对，画油画。对，那这个是直接再溅开来啊，对 ，smearing is more like anybody smear. Have you been smearing something in your life? How about peanut butter, right? Take the knife and spread. Smearing is more like spreading. Spreading like peanut butter on a piece of bread. 花生酱那种感觉，这样子抹它啊。So this is like smearing. So delta function is before smearing, after smearing, now is somewhere there. 想象一下啊，涂面包啊，应该那个番茄酱不是，然后要把它涂满整个表面啊。Smearing versus splattering, fancier way to refer to main lobe versus side lobe. Okay, two verbs.